you for joining us today. My name is Javier Luca de Tena, and today here with my teammate Tsuruhara Tomu-san, we are both server-side engineers at the line messaging dev team, and today we are sharing how we are transforming the line messaging from the active standby disaster recovery model to a fully active multi-data center system. This session is about what we are building and what we have learned so far. This session consists in two parts. I will be talking first, the first half, about the line messaging and the active standby architecture, what limitations that we have faced, and why we have decided to move to an active architecture. He will also be sharing about some of the solutions that we have thought and some of the challenges that we are facing. Then Tsuruhara-san will take over and talk about why we need a new database to make all of this work. For those unfamiliar with the line messaging, it's one of the most widely used messaging platforms in Asia, serving hundreds of millions of users globally and processing billions of interactions every day. It's not only about text messaging. It has voice and video calls, rich media, stickers, and much more, and also a whole ecosystem of applications built around it. Line is a critical communication infrastructure, so reliability and performance are fundamental for us. So here is a simplified overview of our architecture. Clients connect through our API gateway to the messaging backend, which handles all the traffic logic, messaging like messaging delivery, synchronization, social graph, etc. And the backend relies on a storage layer, which is compounded by Apache Acebase for the persistent data and Bulky, which is a Redis fork for the caching layer. All of this is operated in our private cloud called Flava, and so this means all infrastructure is managed by us end-to-end. As the API gateway is already an active component, for today's session we will be focusing on the messaging backend and the storage layer. First, let me explain about the active standby architecture and what are the limitations that we are facing. Our current disaster recovery model is a classic active standby setup. So one data center handles all the traffic. Data is replicated asynchronously to the standby data center, holding a whole copy of the data. If the data center goes down, all the traffic is switched to the standby. This is a very simple approach, and it has worked for us for many years. But this model has serious limitations. Let me give you a real example. So we perform regular disaster recovery drills where we simulate a whole data center failure and validate that things still working. During one of these drills, we discover a core feature has been broken in the standby for weeks. Nobody noticed because the standby never receives real traffic. So here's the fundamental problem. So the standby is invisible. It cannot be tested with real conditions, so it degrades silently. And if you don't want this to happen, maintenance costs can grow quite a lot because every new feature will need disaster recovery support included into the drills and dedicated testing. Failover also requires some service interruption to restart the process or changing the configurations or maybe warm up the cache. And we are paying for a whole data center that it sits there doing nothing most of the time. However, all line core features must work regardless of any data center outage with close to zero downtime. So we ask ourselves, why just not have both data centers as active, sharing everything in an active fashion? So then there will be no invisible standby that silently degrades. Both sides will be always validated with real traffic. No cold start, traffic just shifts to the surviving data center and service continues. That is how we achieve downtime close to zero. But as you will see, this is not easy. So you might think, why not just make both the data center actives and share everything? The problem is, well, physics. Our data centers are geographically separated, so latency naturally increases. So for simplicity, let's say 20 seconds for the whole round trip between data centers. And that compared to 1 or 2 milliseconds that we have in a single region is a big gap and creates very real challenges, as we will see next. The first challenge is data consistency. With asynchronous replication, regions can temporarily see different values. Imagine a write in region A may not be visible yet in region B, causing stale reads. Many services can tolerate this and move in this model, but in a real-time messaging service, many users-facing operations like messaging ordering, friend list, conversation metadata, privacy settings, or group membership, depend on seeing the latest state. And stale read can directly translate into confusing or incorrect behavior for the users. So, and under high load or network problems, the replication lag can grow and the issue will be even worse. So our solution is to adopt a region partition active-active architecture. The key idea is very simple. We assign each piece of data a primary region. All reads and writes for that data are routed to this primary region. And this eliminates the stale read that we have mentioned before. Of course, data is replicated to at least 2 data centers for resiliency. And we also have a third data center that is for storage purpose only to handle consensus and durability. But that will be covered by my teammate Tsuruhara-san later. Under normal operation, both active regions serve users independently. If region B fails, all traffic shifts to region A automatically. Region A was already active and well tested with real production traffic, so we have high confidence that it will work correctly. Of course, there will be additional traffic going to the surviving data center, so we make sure it has enough capacity. We can also partition our data based on the communication patterns. Users naturally tend to communicate with other users in the same geographical area, so their data can live together in the same region. With this, we can keep most of the traffic within a single data center or in the single region, so the cross-region latency penalty is significantly reduced. But you might be wondering, how do we route to the correct region? So to solve this, we are building a new component called that we have named Region Lookup Manager. It answers one question. For a given piece of data, which region is the primary? When the service needs data, it first asks to the Region Lookup Manager which region is the primary, and then the service goes directly to the primary region where the data is always fresh and consistent. The Region Lookup Manager is deployed in every data center as an active-active component, so queries are always local and fast. The region mapping is stored in a consensus-based storage that guarantees mappings are never lost. Even if one data center goes down, the surviving 2 still have the majority and keep serving. We are also adding a caching layer that we believe will be really effective because region mappings change very rarely. But even with geographic partitioning data, cross-region requests are unavoidable. Users in Japan may message friends in Thailand, or maybe we have groups spanning multiple regions. So a single request may need to query data from multiple regions. So the issue is that a single API can trigger multiple sequential I/O operations locally at 1 or 2 milliseconds. Well, it works fine and nobody optimized, right? But across regions, each I/O can take around 20 milliseconds, easily breaking the service level objective and, of course, degrading our user experience. So just to visualize, let's say a group message may require fetching the group information, then the member list, the delivery preferences, maybe privacy settings, client information, sender profile, then maybe store the message and update the inboxes for everyone. This could mean many sequential I/O, making latency a real concern. To address this, we are optimizing IO in different ways. First, we parallelize and batch operations whenever possible, using custom tooling that we have built for safe parallel IO. It sounds straightforward, but proving IOs can be safely parallelized in a high concurrency system like line messaging requires deep analysis of the code paths and distributed traces. Ordering assumptions that held at 2 milliseconds may break in subtle ways at 20. So we also merge data models when it logically makes sense, combining data that always fetch together into a single query. This actually increased the schema coupling, but the latency and the IO reduction, I think it justifies the trade-off. Let me show you the actual impact. So this is our response time service level indicator for group chat messages over time through multiple optimizations. And as you can see, it has been dramatically improved. Sorry. The next challenge is bulky node-to-node replication. And this may require a further explanation. Bulky keeps a buffer of recent writes for replication. Locally, this works fine. But across regions with higher latency can cause replicas to fall behind. When these replicas fall behind, bulky triggers a full synchronization and transfers the entire data set. At the line messaging scale, hundreds of shards could trigger full synchronization at the same time, saturating the network, causing even more replicas to fall behind, and then we have a cascading failure. Full sync is also a resource-intensive thing and can impact the normal traffic handling. And because of all of these reasons, we have decided to not replicate bulky across regions. So data belonging in one region is simply not cached in the other. So imagine region B goes down. Traffic shifts to region A, but region B's data is not cached there. So every request now falls directly into the persistent layer, and it cannot handle all the traffic by itself. Then the persistent layer gets overloaded. Region A starts degrading too, and what we thought it was a single region failure became a two-region outage. We thought about multiple solutions for this, one of them being a bad job to pre-populate the cache. But then we won't be able to switch the traffic until the job is completed. So it will require service interruption, and we'll be back to square one. So what we need is to keep cache warm in the other region continuously and with enough consistency so failover can happen instantly. And to solve this, things like simple read-through cache in the other regions is really not an option, because maintaining real-time consistency across regions without any transaction is not feasible. Transaction algorithms, such as two-phase commit, will add latency to every cache write, not to talk about the amount of complexity it will bring. So we need something different. And what we came up with is a solution with using asynchronous event streaming. For mutable data that uses read-through cache, such as user information or social graph, after our caching transaction algorithm commits into region A, we publish the results into Kafka. A consumer in region B reads it and writes it into the region's B cache. Since Kafka messages can arrive out of order, we use a transaction ID. So we only write into the cache if the transaction ID is newer. If in case of producing an inconsistency, that can happen, it will eventually disappear thanks to a configure TTL. So as you can imagine, this has many edge cases outside the happy path. So the consistency isn't actually perfect. But considering our goal is instant failover, we consider this a fair trade-off. For immutable or write-through cache data, we can use change data capture, where we stream the mutations entirely directly from the persistent layer write-ahead log. We have yet another challenge. The messaging backend is already facing a fair amount of complexity. We have multiple database middlewares, each one with their own APIs, clients, or operational quirks. On top of that, the services are implementing sophisticated caching algorithms, secondary indexes, transactions, fallback logics that cascade through multiple layers. This complexity has made our developers to introduce subtle bugs that in some cases has led to, well, production incidents. Now, we are adding even more complexity: consensus-based storage, multi-data center routing, the region lookup manager, cross-region cache warm-up, and failover handling. Expecting every service team to implement all of this correctly, consistently, and without bugs is probably not realistic. And keep in mind that we have shown today just the high-level overview. So this is why we are building the storage abstraction layer. It sits between the service and the storage and expose a simplified, unified API. Developers do not need to know which region owns the data, how caching is implemented, how warm-up events are produced, or how failover is handled. All of that is handled transparently inside the abstraction layer. This makes migration to the multi-region active-active architecture seamless. Well, not seamless, maybe less painful. So let me recap. We are building region partition active-active system. We have solved the I/O penalty, the region routing, hidden the complexity behind an abstraction layer, the cross-region cache warm-up. All of this gave us the architectural model to achieve almost instant failover and more robust disaster recovery model. But when operating bulky and ACE-based across regions, we found that they have some limitations. They were not designed for native multi-region data consistency. So, to be clear, we are not replacing them. They are amazing tools and will stay for us for a long time. But we need a complementary layer, a distributed data source of a distributed source of truth designed for multi-region data consistency. And that's why my teammate will cover now. We will now switch the speaker. Please bear with us for a moment while we change the equipment.
The speaker will now change. I am Tsuruhara. I will now discuss databases. As the title suggests, I will talk about our decision to adopt Yugabyte DB. As introduced in Javier's part earlier, we are working on the back end of Messenger. We are trying to migrate to a multi-region active-active configuration. I've introduced some of the necessary innovations, but ultimately, the source of truth. A database is necessary. That's the flow. So for this latter half, our goal is to be able to answer key questions like the ones written here. First, we are trying to adopt a new middleware called Yugabyte DB. But why do we need a new middleware for multi-data center active-active operations? I believe some of you might feel that the topic has shifted a bit, so I'd like to explain that part first. The second point is why Yugabyte DB. Especially in Japan, there are many cases where TIDB is adopted. I will now explain why we did not choose TIDB. So, let's dive into the first point. Why do we need a new database? To reiterate, in the first part of the presentation, I mentioned that our Messenger backend would be moving to an active-active multi-data center configuration. There, we needed a database that would serve as the source of truth. we have shown our approach. So, what exactly is a source of truth, if we try to put it into words? This isn't necessarily how it has to be, but it's what we consider the source of truth. First, from an applications perspective, it actually operates across multiple data centers. We want it to appear as a single database. You want, don't you? Also, we want to be able to read the latest data written in any region from any location. Otherwise, it becomes difficult to develop applications. And of course, even in the event of a major disaster where an entire region goes down, without data loss, we need it to operate, and of course, it must have high availability. Therefore, these things are necessary. So for this whole thing, the existing HBase that we are currently using, we will consider whether this can be achieved effectively. Actually, that's what we thought about at the beginning. I will explain the process. First, even if a region goes down, there should be no data loss. We need to perform cross-region replication. This is self-evident. This is something that absolutely must be done. Normally, if you do this, it will be asynchronous, async commit. If done asynchronously, data loss cannot be completely prevented. What does asynchronous replication mean? After the data is written to the source of truth, this means there's a time lag until that replica is created. Then, when a failure occurs, the data updated or added just before that failure will be lost. That would be a problem. So then, should we replicate synchronously? This presents its own set of problems. So, what does it mean to perform synchronous replication? Writes to both region 1 and region 2 are, this means that once it's committed, it's considered a successful write. What this means, in other words, is that, even if region 1 fails, it will lead to a complete outage, and the same applies if region 2 fails. We wanted to increase availability. We have brought it to the region. If we do this, it will actually lower availability. This would defeat the purpose. So, what should we do? If we think about it naturally, well, when it's operating normally, while replicating with transactional locking, if a failure occurs, stopping replication. Let's provide services with the surviving ones. I think so too. We are talking about active/active. This is where fault detection comes in. This must be done automatically. We want to automate that, especially when there are only 2 regions. The automatic failure detection here is important. It's quite difficult. That's it. It is said. I think it's difficult because it's called split brain. Because there is a problem. What kind of problem is this? Even though both Region 1 and Region 2 are operating normally, this is a failure, like the network between them being disconnected. This is what happens. They recognize each other as being in a failed state. It assumes it is the surviving primary. If we continue to accept writes from users in that state, then, when replication is resumed, then it becomes unclear which data is real or which is correct, making it difficult for business to continue. It's quite difficult. So, what should we do? Generally, split brain is, as shown in this diagram, by bringing in a third region. This problem can be solved by making it act as an arbitrator. We introduce the third option, which prevents split brains. Even with this, subtle issues still remain. First, even with this configuration, all write traffic will still be because it flows between region 1 and region 2. If the network here goes down, a failover will occur without interruption. When a failure such as round trip time doubled occurs, the query latency for all database writes would double. For latency-sensitive services, that's quite a frightening prospect. Therefore, this is also somewhat unacceptable. Also, the failback process after a failover is not trivial. There are still issues. So, what should we do next, is the question. I imagine it seems quite difficult and complex. Therefore, the answer to the first key question is, that's where, well, HBase and its replication. By making good use of it, somehow multi-data center, active. Well, I don't think it's impossible. We cannot succeed without creating something quite complex ourselves. This is why we arrived at this conclusion. Existing ones, so to speak, do that a little better. It's about whether it would be better to introduce a watching room. I hope that makes sense to everyone. Now, let's hear about this. I think there might be people wondering, why not just use Cassandra? I won't go into too much detail, but I'll briefly supplement this point. Cassandra, if it performs quorum reads and writes, when the brain is functioning normally, consistent reading and writing are possible. As Cassandra itself states, it provides eventual consistency. There are some corner cases where consistent reads and writes are not always possible, and that's why. How can we use it as a source of truth, which I will introduce later? We believe that a new type of middleware like this would be better. I've been trying hard to explain the issues so far, so what do we do about this? What we want to do is, it can withstand region-level failures and high availability. Such replication is necessary. So, what should we do? Actually, in the academic world, in the 90s. So, it's about state-machine replication, is called. There are several algorithms, and it is known that using them allows for highly available and fault-tolerant replication. We believed it would be best to use a database that implements this. So I know keywords like Paxos and Raft. That's right. It's sometimes called that too. Yes. Therefore, databases that actually implement such algorithms are available. There are already several in the world. I've listed about 4 based on my own discretion, and I think many of you might have heard of Cloud Spanner, the one at the top. This is a Google product that implements Paxos. It is a pioneering database in this field. However, for various reasons, it is difficult for us to use it. Since it can only be used by Google Cloud users, we have excluded it from our selection this time. The second one, CockroachDB, I think this is also a very good product, but during our selection process, there was a license change. Since it is no longer open source, we have excluded this from our selection as well. And so, from here, Yugabyte DB and TADB, which are implemented with Raft. Let's compare them. First, I will present 2 rough architectural overviews, but since these are overviews, actually, when abstracted to this extent, both are generally the same. Roughly speaking, there's something like a command system called the control plane. There are 3 or 5 machines. The data plane nodes that it orchestrates. This is a distributed database with many instances. At this level of abstraction, HBase actually has the same structure, but the biggest difference is that this is where the data is replicated. It uses Raft. For distributed processing, it employs a method known as sharding. Many of you are probably familiar with sharding. Logically, a single table. The values of specific columns, which are called primary keys or sharding keys, as a standard and splitting it into smaller units. Here, for convenience, we will call them tablet. Then, for each of these smaller divided tablets, a separate one is used, so that the data processing nodes can handle it. It's a way of distributing Mafka and TDB, Raft, TiDB, and Yugabyte DB. For each tablet, replication is performed using Raft. Here, there are 3 nodes in 3 regions. I will briefly explain how it works based on this premise. If I were to explain Raft in its entirety, we would run out of time, so I will just give you a general idea. Raft forms a group of 3 machines, and first within that group, this means electing a leader node. We will do it. Data read and write operations are basically performed on the leader. Then, when we tell the leader to write the data, the leader first writes to its local disk. The same content will be sent to followers. It will be forwarded for writing. And whichever of the followers, if it can be written to disk, it's considered successful at that point. Is that clear? It's a bit strict, but yes, it's that kind of algorithm. Therefore, in this diagram, if either region 2 or 3 is active, will succeed. Even if one network is slow, if the other can be accessed at normal speed, and the query latency also does not increase. That is to say, then you might think, what happens if the leader dies? In that case, 2 of the surviving followers would be required. It also runs a leader election algorithm. One of them becomes the new leader and continues processing. If you're interested in the details, let's discuss it again later. So far, I've discussed the common architectures of TDB and Yugabyte DB. What I've been discussing so far is to both. This is where it applies. However, there are also quite a few differences in the details. The biggest difference from an application developer's perspective is that TKV is MySQL compatible. Yugabyte DB is compatible with PostgreSQL. So, when migrating existing applications, the difference is quite important. The backend for the messenger is now. We use HBase. Neither is compatible. This is actually not very important to us. The difference in timestamp Oracle allocation methods below it becomes quite important, so I will explain it briefly. So, what exactly is a timestamp Oracle? Both TiDB and Yugabyte DB are databases. Even if many clients access it simultaneously in a consistent order, it is necessary to process them. To achieve this, usually for each transaction, a timestamp or a unique ID is issued to determine the order. However, this is with a distributed database. How it's done is not that obscure. Some of you may have heard of TrueTime in Cloud Spanner. In the case of TDB, it uses something called Timestamp Oracle. This is the only one in the cluster. You would run a process called Timestamp Oracle. It takes sole responsibility for issuing timestamps. This ensures a consistent order. It can be allocated. It's a simple idea, isn't it? In the case of Yugabyte DB, it's not that style. It is called hybrid logical clock. When communicating between nodes is incremented. It's like a combination of a logical clock and a physical clock. Why this works is quite intuitive. I don't think it's possible. The point here is that Yugabyte DB, on the other hand, does not rely on a centralized component like a timestamp oracle. Therefore, we have briefly reviewed the architecture. From here, which one is actually, I would like to introduce the selection process that determines which one to use. We use these three criteria as the three pillars for our selection. The first is whether the feature set implements the functions we need. The second is resiliency. To begin with, what we want to achieve is an improvement in our disaster recovery environment. How quickly we can recover from a failure is a crucial point. The third point is performance. Since this is a database, obviously, the faster it is, the better. Today, I will primarily focus on performance. So, performance factors are service. We have an SLO at this level, so we'll keep that in mind. Benchmark tool YCSB. Next is a component we call replayer internally. This is a tool that reproduces production environment workloads. We evaluated these two. The test environment is as shown in this diagram. We distributed 9 data plane nodes across 3 data centers. We have configured a cluster of 5 nodes. There are 5 control planes between each network. The round trip time is 30 NAMs. We are adjusting it to be that way. So, we tested this in such an environment. Let's quickly look at the performance graphs. This is a production environment. This is the query latency, assuming a certain production environment. So, since it's latency, the lower part of the graph is better. So, if you look at this, the query is very simple, and both TKV and YugabyteDB are responding in around 2 milliseconds, so there isn't much difference here. Of course, there are patterns where differences emerge. This is an update to the same table, but TKV takes about 35 milliseconds, whereas, even for 1 gigabit, there are cases where a difference of 140 milliseconds can significantly impact performance. So, we drew many graphs like this. We made a comparison. It's obvious if you think about it, but depending on the table schema and the query, the results were completely different, and it was not the case that one was overwhelmingly superior to the other. However, TKV is faster for writes within the scope of our benchmarks. It was more of a tendency, if you will. Hearing that, you might think, then TKV is fine and cheap. And TDB is, there's one architectural point of concern. That is the timestamp oracle we discussed earlier. TKV uses a timestamp oracle, a process that issues timestamps and exists as a single instance in the cluster. So, in this diagram, the circle on the left, that would be the leader of the control plane node. This means that, as shown in this diagram, depending on the client's location, there will always be patterns where the communication to retrieve that timestamp oracle becomes cross-region. This has an inner round trip time of 30 ms, so there should be a corresponding penalty. This means that query performance should also degrade when I looked into it. This graph shows the results as predicted. This is the same latency graph as before. So, what about the left side of the vertical line in the middle? This is the performance when the client and the timestamp oracle are in the same data center. At the vertical line, this is the timestamp oracle process, named PD. We move the PD to a remote data center, and the latency is sharply increasing. Cloud spanner. The previous one was the latency for inserts. The same applies to select. 50 ms or so. Latency increases. So, what about reads? Actually, there's a pattern where this doesn't happen. That's interesting, but that's for another occasion. To summarize the performance, though I haven't discussed throughput at all, as a result, there wasn't a significant difference in throughput. Therefore, neither of them has a significant advantage in terms of latency. Yuga Bagi. Light writes can sometimes be quite slow. TKV was from earlier. Regarding timestamp for reads, there are times when it's tough. What should we do in response to this? Oh, before that? Regarding resilience, I will just briefly present the results. Let's keep the results in mind. KO University has experienced various strokes. We measure the time it takes to recover from a crash state, and Yugabyte DB has shown superior results in this regard. In particular, TKV is designed to handle the timestamp oracle process we just discussed. Once it occurs, recovery takes a long time. Given all of this, the question is which one do we choose? The answer is already in the title. Ultimately, our goal was to improve disaster recovery. Next, what are we going to use this for? As introduced in the first half by Havel-san, one application, called the Region Lookup Manager, returns an object in the region where it is primary, which is its mapping. These are quite read-heavy workloads. Therefore, as a result of various comprehensive considerations, we chose Yugabyte DB. We decided to select. Does that make sense? So, as for the 30% that I mentioned, the answer to the key question I first presented, why do we need a new database, is as follows. Existing HBS, or it becomes extremely complex and difficult to implement active-active multi-data center. That's what it comes down to. Why Yugabyte DB was a question often asked, and the comparison was made with TDB. As expected, TDB's timestamp oracle, which is an architectural, the bottleneck was caught, and in the end, we decided on Yugabyte DB. Roughly speaking, that's how it is. Finally, to summarize the entire presentation, what we aim for is, I would like to conclude by introducing the active-active multi-data center configuration. Basically, we use data centers in two regions as active ones, and they receive user requests. So, the stateful part, the database part, we are using Yugabyte DB as the source of truth, while also employing techniques such as the partitioned active-active approach that I discussed in the first half of my presentation. It also uses HBase to handle write-heavy workloads. It is assumed, of course, where caching is needed, we will use a cache. Ensuring that consistency is a difficult problem. We believe that caching can be handled using the techniques introduced in the first half of the presentation. This makes the storage layer complex. Right. To avoid directly implementing such complex logic in the application, we use a storage abstraction layer as an idea. Yes, roughly speaking, we plan to create it. We are aiming for something like this. That concludes my presentation. Thank you for your kind attention.